Alright, EP Stat students, this 4.2 section is probably going to be very long. There's going to be a video in there, so bear with me through all of this. So we have observational studies versus experiments. Sample surveys gather information about a population without disturbing the population. This is one type of observational study. An observational study observes individuals and measures variables of interest, but does not attempt to influence the responses. An experiment deliberately imposes some treatments on individuals to measure their responses. In experiment, we have an explanatory variable, which is what we're controlling, and a response variable, which is whatever comes out. The November 2009 issue of Nutrition Action discusses what the current research tells us about the supposed benefits of soy. For a long time, scientists have believed that the soy foods in Asian diets explain the lower rates of breast cancer, prostate cancer, osteoporosis, and heart disease in places like China and Japan. Is this describing an observational study or an experiment? All they're doing is asking. It doesn't say that we tried to influence this at all. It's just an observational study. Several different studies randomly assigned elderly women to either soy or placebo, and none of the studies showed that soy was more beneficial for preventing osteoporosis in Asian cultures. Is this describing an observational study or an experiment? Well, it's an experiment because they randomly assigned these women to either one or the other, trying to find out what happens. We still don't know. It could be due to genetics, other dietary factors, or other difference between Asian and non-Asian cultures. So even though we ran this whole experiment, it doesn't tell us exactly what's going on, but it gives us an idea. So what we have is a lurking variable. That's a variable that is not among the explanatory or response variables in a study, but that may influence the response variable. So other things in diet, maybe genetics, are lurking variables. We don't use this term very often anymore. Confounding is really a better term because it's a more umbrella term. Confounding occurs when two variables are associated in such a way that their effects on a response variable cannot be distinguished from each other. Experiments allow us to determine causal relationships. Observational studies do not, due to lurking and confounding variables. So going back to our example, remember in this one they had women from some countries and then women from China and Japan. This was an observational study. They believe that this soy had some issue, but there's a chance that genetics and all these other things could be in there. However, if we just randomly assign any women of all different races and all different backgrounds and things of the same age, then we can control and get rid of some of these lurking and confounding variables. So then this soy will have a better chance of coming out as a positive response. Does eating dinner with their families improve students' academic performance? According to an ABC News article, teenagers who eat with their families at least 5 times a week are more likely to get better grades in school. This finding was based on a sample survey conducted by researchers at Columbia University. Was this an observational study or an experiment? Well, this was an observational study as well. They just sent out a survey, so they did not try to control for these lurking variables. The explanatory variable was the eat dinner together 5 times a week, and the response variable was the student's grades. Explain why such a study cannot establish a cause and effect relationship. Well, think about all the confounding variables in here. What are other reasons that they would eat together or not eat together? Well, if you think about people who may have many jobs that might be living in poverty, they might not be able to eat together. So there's a lurking variable right there. There could be many other lurking variables, but there's just one for an example, and you can explain that. So now we have the language of experiments. We have treatments. So a treatment is what's imposed on an experimental unit. So an experimental unit is what gets the treatment. Okay, a subject is an experimental unit. When we're talking about people that are experimental unit, we call them subjects. But other things that maybe Coke cans or anything that gets a treatment is an experimental unit. A study published in the New England Journal of Medicine compared two medicines to treat head lice, an oral medication called ivermectin and a topical lotion containing malathion. Researchers studied 1812 people in 376 households in 7 areas around the world. Of the 185 households randomly assigned to ivermectin, 171 were free from head lice after 2 weeks, compared with only 151 out of 191 households randomly assigned to malathion. What are the treatments? The treatments are the medications. The experimental units are people, so subjects, okay, because they're getting treated for the head lice. And the explanatory variable is which medication. And the response variable is lice or not. How to experiment badly. Good experimental designs are essential for effective experiments. Many students and statistic teachers regularly consume caffeine to help them stay alert. Thus, it seems plausible that taking caffeine might increase an individual's pulse rate. Is this true? One way to investigate this is to have volunteers drink some cola with caffeine, measure their pulse again after 10 minutes, and calculate the pulse rate. What do you think? Well, one issue we have right off the bat is if we have volunteers, right? We have voluntary response bias. We don't have any random assignment. What we should do is we should randomly assign half of the people to a caffeine group and half of the people to a placebo group, and then calculate the increase in pulse rate. Good experiments must have some comparison to prevent lurking variables. This does not compare the different pulse rates. What we need to experiment well is that random assignment. Let's say we do the caffeine experiment with the 16 students that are taking AP Statistics this year. How would you decide who would get each treatment? Well, if we had slips of paper, the first 8 would go to the caffeine group, and then the other 8 would go to the placebo group. With a random digits table, we would have to take 2 digits at a time. So we would assign the numbers from 01 to 16, and we would pick the first 8 in the caffeine and the second 8 in the placebo. With the random number generator, same thing, we would just be able to assign them 1 to 16 and use our randint. We should always draw a picture of our experimental design. So we have our 16 volunteers. We have random assignment. We randomly assign them into group 1 and group 2. And then group 1 gets the caffeine, and group 2 gets the placebo. And then we can compare our results. In a completely randomized design, the treatments are assigned to all the experimental units completely by chance. So what we did, we have our random assignment. A health organization wants to know if a low-carb or low-fat diet is more effective for a long-term weight loss goal. The organization decides to conduct an experiment to compare these two diet plans with the control group that is only provided with a brochure about healthy eating. 90 volunteers agreed to participate in the study for 1 year. Outline a completely randomized design and write a few sentences about how you would implement it. Draw a picture. So we have our 90 volunteers. We're going to put them into 3 groups. Group 1 is going to have 30. Group 2 will have 30. And group 3 will have 30. What I forgot to mention is we need our random assignment into those groups. Group 1 will get treatment 1. Group 2 will get treatment 2. And group 3 will get the placebo. And then we'll compare our results. Okay, to write our paragraph, I'm just gonna tell you, we'll have our 90 volunteers, we'll randomly assign them. You want to explain how you randomly assign them. So you would maybe say the first 30 people chosen by your random number generator would go into group 1, the second 30 unique people would go into group 2, and the remaining 30 people will be placed in the placebo group. And then you'll compare your results. You could say a little more than that. There are 3 main principles of an experimental design. You need your control for any lurking variables that might affect the response. So using a comparative design ensures that only the systematic differences between groups is the treatments. So when we control, this is where we talk about having our placebo versus our treatment. Need that. We need random assignment, so using chance to assign the treatments helps create roughly equal groups receiving each treatment. What that does is it controls for those confounding lurking variables because they're equal groups. And the third one is replication. We need to use enough experimental units in each group so that differences of the results between groups is definitely not from chance. For example, if we only had 5 people in a study, and we assign them into a group of 2 people and a group of 3 people, that's not really enough to convince us that the treatments are doing something. Does regularly taking aspirin help protect people against heart attacks? The Physicians' Health Study was a medical experiment that helped answer this question. In fact, the Physicians' Health Study looked at the effects of 2 drugs, aspirin and beta-carotene. Researchers wondered whether beta-carotene would help prevent some forms of cancer. The subjects took this experiment were 21,996 male physicians. There were 2 explanatory variables, each having 2 levels, aspirin and beta-carotene, yes or no. Combinations of the levels of these factors form the 4 treatments shown in figure 4.6. 1/4 of the subjects were assigned at random to each of these treatments. This is kind of similar to an AP test question that we had, but they didn't tell you the groups. So here are the 4 groups. This first group had beta-carotene and aspirin. The second one had beta-carotene but not aspirin, so that was a placebo. This one did not have aspirin, but it had beta-carotene, and this one had neither. On odd number days, the subjects took either a blue tablet that contained an aspirin or a dummy pill that looked like and tasted like aspirin, but had no active ingredients. On even number days, they either took a capsule containing beta-carotene or a placebo. There were several response variables. The subject looked for heart attacks, several kinds of cancer, and other medical outcomes. After several years, 239 of the placebo group, but only 139 of the aspirin group, had suffered heart attacks. This difference is large enough to give good evidence that taking aspirin does reduce heart attacks. It did not appear, however, that beta-carotene had any effect on preventing cancer. Explain how the 3 principles of the experimental design were used. We have our control group. We had controls with both beta-carotene and aspirin, those placebos, so we could compare. We had random assignment. We randomly assigned them to either take beta-carotene or aspirin. They looked at those 4 treatment groups, this 1, 2, 3, and 4, and they had replication. There was 21,000 people in this study. So that's plenty of experimental units, or subjects in this case because they're people, that we can trust the results. How can experiments go wrong? Well, sometimes having a treatment is enough to influence results regardless of the treatment. So we talked about placebos, but we haven't talked about this placebo effect. Sometimes people believe that placebo's actually working. It's not supposed to, but it actually does. So I have this really awesome video that I'm going to show you right now. That's why this video is going to be really long, to kind of explain that.
Now, you've all heard of the placebo effect before, when something with no known therapeutic value can actually make people feel better. It's a great trick our minds play on us, that by believing and expecting something to work, it actually does. But what's weird is that the strength of the effect can differ for some really strange reasons. For example, the same placebo can treat pain half as well as aspirin, while at the same time treating pain half as well as morphine. Morphine's a much more powerful painkiller, but a placebo is half as effective as both? Saying a placebo will reduce pain reduces pain, but saying that the same placebo will increase pain increases pain. Believing that a placebo will make you feel better will make you feel better. Believing that it won't has the opposite effect. Now, placebos aren't just pills. They can be creams, injections, surgeries, or drinks. You can even get placebo buttons. They don't actually do anything, but they sure as hell make you feel like you're in control. But not all placebos are equal. The effect of the placebo is bigger when the pill itself is bigger. Or if you have 2 instead of 1. Or 2 once a day instead of 1 twice a day. And a capsule will usually beat a pill. And a syringe will usually beat a capsule. And anything with a big ass science machine can outperform any of them. A plain pill works worse than a branded one. A discounted pill works worse than a pricey one. And even a pill in a plain box does worse than one that's all shiny and shit. Placebos that are blue work best as downers, and placebos that are red are better as uppers. Studies have shown that people who take their meds on a regular basis are less likely to die than those that don't, even if those meds are all placebos. You can even get addicted to placebos. In one study, a group of women took placebos for more than 5 years. 40% of them suffered withdrawals afterwards. In fact, the effect of placebos can be so strong that some people want them banned from sports. But I mean, how would you even test for that? Placebos don't even seem to work from place to place. For example, in Germany, using a placebo to treat ulcers works better than anywhere else in Europe. But using a placebo that treats hypertension doesn't work nearly as well as it does for its neighbours. Now remember that all of this is about comparing things that both have nothing medically effective in them, which goes to show that a placebo isn't about what's in it, but about the beliefs that we load onto it. Our minds create the medicine, and that is pretty freaking weird.
So now that we're all good on placebos, we have the single blind and the double blind. You may have heard these before. Single blind is when only one person knows, typically the doctor or whoever's giving the experiment. So a problem with this is often when we talk like teachers who think that their students are going to do better, those students do better. That's the single blind study. The double blind is when neither the person giving the treatments or the subject knows. So neither know who gets the treatments. So inference. If we think back to our smelling Parkinson's lady from the beginning of the year, can Joy Mills smell Parkinson's? Why or why not? Well, we don't know. We can't say that she does or doesn't. So we said we have reason to believe that she does. So the statistical significance is when we have enough statistical evidence we believe something influenced our response. So with Joy Mills, we believed that she's smelling something, or there's enough evidence that she's not just guessing. But we can't really say that she can smell Parkinson's. We'll have to use something else. The statistical significance is only one small piece of many, many, many things that people use in studies. It's not the end all be all. Blocking is a different type of experimental design. So suppose researchers want to test whether a new detergent for clothes that requires hand washing cleans better in warm or cold water. They decide to perform an experiment using numerous pieces of dirty laundry as the experimental units. The response variable is a cleanliness rating on a scale from 0 to 10. How should researchers deal with the fact that light-colored clothing tends to come cleaner in warm water? They could use a completely randomized design and hope that the random assignment distributes the light-colored clothing evenly between cold and warm water groups. Even so, there might be a lot of variability in cleanliness ratings in both groups due to the color of the clothing. This lurking variable might make it difficult to detect a difference in the effects of treatments. What should the researchers do? Well, the researchers should separate light and dark clothing and then run their treatments. So we'll draw a picture of this. So we have our clothes. We separate them into the light and darks. Now we do our random assignment. So now we can randomly assign our detergents. And then we'll randomly assign our dark clothing. And then we'll compare. So blocks in a randomized block design. So a block is a group of experimental units that are known before the experiment to be similar in some way that is expected to affect the response to treatments. In a randomized block design, the random assignment of experimental units to treatments is carried out separately within each block. So our block is light clothing and our other block is dark clothing. This is really similar to stratifying, but this is not sampling, this is an experiment. Women and men respond differently to advertising. Researchers would like to design an experiment to compare the effectiveness of 3 advertisements for the same product. Why would a randomized block design be preferable to a completely randomized design? Well, the block is going to take into account the men and women, the lurking variables. We would get equal groups for our completely randomized design, but we could get a group of men and a group of women and then randomly assign, and we can get better and more information as to what this advertising is going for, because the advertising might be geared towards men or women separately. I'm not going to draw a picture or outline this in this one. Basically, I'm going to take my 300, I'll group them into 180 men, 120 women, and then I will randomly assign each into 2 groups with my treatment and my placebos. Matched pairs is a special one that's going to come up every once in a while. That's something I find kind of interesting. In a matched pairs design, similar experimental units or the same experimental unit receives both treatments and the results are compared. The order of the treatments can influence the response, so we randomize the order for each of the experimental units. So what this is going to look like is we have our volunteers. We randomly assign them into 2 groups, Group 1 and Group 2. Group 1 is going to receive treatment 1 first. and then treatment 2, which may be a placebo. Group 2 is going to receive treatment 2 first, then treatment 1, and then we compare our results.